Hello everybody, we are back live with another AP Physics 2 review video, and today we are answering a question posed by a very famous songwriter, and that question is, I'm paraphrasing, freaking magnets, how do they work? So we're talking about magnetism and everything that goes along with that. So first, let's recall that there are two kinds of magnetism. There is magnetism created by naturally inherent magnetic materials. We call these mostly ferromagnets. So here's our big block of iron. This is ferromagnet. And like all objects, this ferromagnet is made up of atoms that have a bunch of electrons in them. The way a ferromagnet's electrons are ordered means that it always has a net spin. The last electron in those orbitals has a spin that all goes the same way. So this excess electron spin, they all align with each other, and when they do, they add up and they create an overall magnetic effect. So here we have sort of aligned electron spin. Electrons are not actually spinning, they just have a quantity that happens to have the same units as angular momentum. Quantum mechanics is all very confusing, but this spin is what causes the overall magnetic properties here. So what happens is all these electrons are aligned with each other, and in this direction is going to cause a magnetic field to come out of the top of this magnet. And likewise, at the other end, the arrows are still pointing to the right, those field lines are going to point inwards to the other end of the magnet. So this first kind, this ferromagnetism, is caused by a line electron spin. We have a field coming out at one end, we have a field going in at the other end, and a magnetic field has to connect. So these lines loop around to either side of the magnet, so that it comes out of the magnet on one side and it ends on the magnet on the other side. These lines are connected too, but I don't feel like drawing them. So all of these lines have to connect. Any magnetic field must essentially be a closed loop of some sort. So here's our ferromagnetism. We call the side where the magnetic field is coming out, that's our north pole of the magnet, and the other end is our south pole of the magnet. Makes sense. So our north pole, our south pole, magnetic field always goes out of the north pole and into the south pole. So that's our ferromagnet. We can also get magnetic fields stemming from a change in charge over space. So if I have a change in the amount of charge over some spatial dimension, this change in charge, and therefore change in electric field, will give us a magnetic field. So change in electric field in space creates a magnetic field. And then we learned in induction that a change in a magnetic field causes a current, which is an electric field. So changes in electric fields cause magnetic fields, changes in magnetic fields cause electric fields, and they all build off each other. That's the principle behind electromagnetic waves. But here today we're just going to focus on the fact that a change in electric field creates a magnetic field. The simplest way to do that is through a current. So here's our wire. It's going to be flowing out of the page towards you. So the little point here represents that. This we're going to draw sort of three-dimensional kind of shape here so that we see this wire coming out towards you. So the current direction is flowing out towards you. And because we have charges moving through this wire, those moving charges change the nature of the electric field at any point in space throughout time, and that creates the magnetic field. So as the current flows, we get a magnetic field that forms. And again, just like the one over here, it has to be a closed loop. So our closed loop for this magnetic field, if our current is going out towards us, we point our thumb along that direction and curl our fingers around. And so our magnetic field is going to curl around in the counterclockwise direction. So B field curls around wire. With a circular shape. So depending on which way the wire is flowing is going to determine whether that circular shape loops around counterclockwise as it does here, or clockwise if the wire were going in the other direction. So our right-hand rule, it's actually the second right-hand rule we introduced, but I'm going to introduce it first here. So why not? Right-hand rule number 2 says thumb is current, fingers loop around to give B field. And this works for any old wire. If I have a wire that's going to the right, well, I'm going to put my thumb as the current there going to the right. Like I'm hitchhiking here, and I'm going to curl my fingers around the wire. I'm going to grasp the wire in my hand, and I can see that, you know, above the wire, it's going to come out of the page. As I loop my fingers around the other side of the wire, my fingers have to dive back into the page, and so now we're going in over here. And then if we were somewhere in space over top the wire, we got to think 3 dimensions here, then my field is kind of, you know, looping from out to in, and it's directly down the page over top, and would be directly up the page if I were underneath the wire. So I can draw those little vectors sneaking out from the bottom of the wire here to connect all the dots here. There is a circular field looping around this wire. So I was here, our B field loops around like so, in to out and then back. So we now know that ferromagnets, like hunks of iron and current carrying wires, can in fact make magnetic fields, and things that make magnetic fields exert forces on other things that make magnetic fields. So just like if we had 2 point charges, positive and a negative, this makes an electric field, this other charge makes another electric field, and therefore these things can both interact with each other. So electric fields interact with electric fields, whereas things that make B fields interact with other B fields. If I have 2 magnets with a north and a south pole, there's going to be an attraction between this other magnet with a north and a south pole, and these will attract in the same way. So B fields interact with other B fields. And they do so by exerting forces on each other. So our next goal is to translate what happens when a magnetic field interacts with something else that produces a magnetic field, and what do these forces look like. So we said, let's look at the simplest case. Moving charge in a wire. We have a bunch of charges moving around. That creates a magnetic field. So the simplest case of that would be just one charge moving around. This charge moves with a velocity v, and that is going to be put in some kind of magnetic field. So here's our B field now, going up the page, vector v. So this uniform field B, this charge is moving to the right in that field, and we want to know what is the force acting on that particle. Well, we can find the direction of that force by applying our right-hand rule number 1, We take our thumb, we point it in the direction of V. Our fingers, they are the direction of B, the B field, and now the force is shooting directly out of my palm, up, right, out at you. So in this case, the positive charge is going to be deflected upward out of the page in this case. And if this field is like permeating in 3 dimensions, it will continue moving in a circular trajectory as it moves in a different direction with each little step. So right-hand rule number 1 says your thumb points in the direction of the velocity. Your fingers are the B field. And therefore, if you've done this all right, the force vector shoots out of your palm. So you can always find the force vector by applying this right-hand rule. If you are missing one of the other forces, maybe you don't know the B field, but you know that this particle is going to the right, and I know that it's being deflected upwards, I can figure out what the B field has to be by just sort of making my thumb and palm match what's going on. So if I knew V was going to the right and I knew my force was coming out of the palm, the only way that can happen is if the B field's pointing up the page like we drew it here. So you can apply, sort of assign the roles of your hand to these different vectors here, and you'll always be able to figure out the missing vector that you need. So that's how we find the direction. It's worth noting that if our displacement instantaneously, if there were no field here, our instantaneous displacement would be to the right in the same vein as the velocity vector. Our force is perpendicular to that going up. And so because V is perpendicular to F, and therefore that implies that the instantaneous displacement is perpendicular to F, this means that if we go back to our definition of work, F delta X cosine theta would be 90 degrees, and therefore the work done would be 0. So magnetic forces do no work on charged particles. So it's kind of this weird thing because of this resulting perpendicular or circular motion. Magnetic forces do no work. They're like high school seniors in May. They don't do any work. So what does this force depend on? Well, let's think about it. If the charge is stronger, its natural electric field is going to give more of an impact on wherever it is. So when it moves, that change in electric field is going to be stronger. So it has to depend on the charge. If it's moving faster, then the rate at which it's changing the field in space is going to increase. So it has to depend on the velocity. And it has to depend on the magnetic field itself. If the magnetic field is stronger, it's going to be more readily able to distort the path of the charge. QVB. If we want to be pedantic here, we'll add the sine theta, which is specifically the angle between the velocity vector and the magnetic field vector. If these two things are exactly perpendicular, then that's going to be the maximum amount of force because sine of 90 is 1, and that takes the maximum value. If it's anything in between, then it'll be weaker. And if they're completely parallel, if I tilt this velocity vector to go up with the B field now, if I try to do my thumb and my fingers, they all close up on each other and you don't get any meaningful force out of that. So if V and B are parallel, then sine theta is 0 and the force exerted will be 0. So a charge in a field you get maximum force when V is equal, not equal, V is perpendicular to B. And this also results in a circular trajectory. Here I'm going to draw the magnetic field going into the page. And my velocity is going to be directly into the field this way. As it goes in, my thumb points to the right, my fingers point down, and it's going to be initially deflected upwards. So it's going to start going upwards, but then its velocity vector is changed to be more in this direction, the combination of its original inertia and the magnetic force pushing it upwards. Now I apply the right-hand rule again. My velocity is going up at an angle, my finger's still going down, so now the force pushes it a little bit this way, perpendicular to its original direction. And so it's going to keep changing its direction and move in a circular trajectory while that's happening. If V makes an angle that's not 90 degrees, let's say an acute angle, with B, then we get a helical trajectory. It's still going to move in a circle, but the fact that there is a component that the magnetic field does not act on, so now we're going in this way, where now I have a component of my velocity that is, doesn't make sense. Let's do it this way. Be easier to show. Now I've got a velocity vector that goes this way. If we were going directly up the page, it would be pushed directly down into the circle. So there's still going to be a bit of, it's going to act on this component to make it go into the page and therefore make a circle in and out of the page. But it's also going to have this component here that the magnetic field is not going to act on at all. So it's going to sort of loop around this field line while still moving to the right. So that's our helical trajectory. It makes like a spiral as it goes around. And if V is parallel to B, then it will continue with same velocity. So that would be, here's our B field going up. Our velocity vector is right in there. Right-hand rule just kind of contorts our hand around with no meaning, and this velocity is going to continue straight on its course between these field lines as drawn here. So these are the three possible cases. We get the maximum amount of force when V and B are perpendicular. We get something in between and a nice helical trajectory when it's not between 0 and 90. And if we're at exactly 0 degrees between V and B, we'll continue with the same velocity and there will be no magnetic force. We can extend this idea of a charge being influenced by a magnetic field to a wire being influenced by a magnetic field by looking at not F equals QVB, but instead we are looking at F equals ILB. I is the current here. This has units of charge per time. This length here is sort of the length of the wire that is exposed to the magnetic field, and B is still just the magnetic field. This L here gives us a unit of length that is present in the velocity here. So we kind of just sort of swapped where this time unit is going to be. This time unit is with the current for a wire, but with the charge, it's for the charge's velocity. And so the current is basically just a measure of the velocity of a bunch of charges flowing together. So here is our L over T. Here is our Q, and we've just sort of swapped the T, which partner it goes with, to build a different formula. So this is for a current carrying wire. And it's the same sort of thing. My wire is going to the right, and my field direction is going up. Right-hand rule is going to apply the same exact way, and this thing is going to be pushed upwards out of the page. F comes up. It's of use to quantify. We've talked about how the particle moves in a circle. We can connect this to uniform circular motion, where now the magnetic field is playing the role of a centripetal force. So we can equate mv squared over r to qvb. I can solve for whatever I want here. Usually the important thing is the radius of the circle that it's going to make. And so we can rearrange this. I get mv squared, basically one of those v's goes away, over qb. And this allows me to figure out how different sized particles or different mass or charged particles are going to move in that electric field. So heavier particles are going to make a larger radius because they have more inertia. It's harder to push them around in a circle. If you're going faster, likewise, you're also going to have more inertia, and therefore you're going to make a wider turn. It's kind of like if I'm going faster, it's harder to turn the car around a tighter curve, essentially. If I have more charge, the magnetic field is going to interact with it more strongly, and it's going to bend it into a tighter curve. And likewise, if my field is stronger, I can get some more bendiness out of that as well. So this is our sort of cyclotron radius. It's the radius of the circle a charge will move in a magnetic field. One last thing to sort of quantify here. We've said that current carrying wires make magnetic fields is what we're talking about. So here's my current. We've already said that this is going to make a counterclockwise magnetic field around it. But the strength of this field is going to die off as you get further and further from this wire. So the B field from the wire is this constant mu naught. Mu naught is a nice, easy to remember 4 pi times 10 to the minus 7 units you don't need to know. The strength of the current is going to determine the strength of the magnetic field, and this is over 2 pi r, which is literally the circumference of the sort of loop of field at that distance away from the wire. So as I get further away from the wire, further out in radius, I still have these circular loop going in the same direction, but it gets weaker as you get further and further away from the wire. So this is our magnetic field from a current carrying wire. If I want to find the force between two wires, well, I got to apply my force on a wire, which is filled ILB, but now I'm going to replace this magnetic field from the other wire. So this is, wire 1. This is going to be for wire 2. So I'm going to make that substitution mu I1 I2 over 2 pi r, where now r literally represents the distance between the two wires. Wires, just like kind of north and south poles, they can attract or repel. If they're going the same way, well, if we apply right-hand rule, the B field from this first wire, that's going to loop around and over on wire 2. Let's label them 1 and 2. Over at wire 2, the field is going into the page at this point. So the B field that wire 2 experiences is in the page. Now we apply our other right-hand rule. This one goes up, this one goes in, and it actually looks like these are going to attract because the force directed on wire 2 is to the left, towards the other wire. We can apply the same sort of logic to make sure it pans out for wire 1. Well, I do my field right-hand rule, and I get that the field is going out of the page. Points here. Wire's going up. To go out of the page, I have to contort my hand all the way this way, and my palm points to the right. So here we have wires in same direction. And my pen appears to be dying at this point. Good thing we're almost done. Wires in the same direction will attract, and I'll let you do it on your own for 2 wires going in the opposite direction to show that they repel. All right, so we have covered all the ins and outs of magnetism and magnetic forces. We are almost there. Keep pushing. AP exam is on the way. See you next time.